You ever see a chemical name and just think, wow, that looks like an alien language? It seems totally random and impossibly complex. But what if I told you it's not random at all? It's actually a code, a hidden language with a system that's surprisingly logical. And today, we're going to crack that code together. I mean, look at this thing. 4S, 5E, 4,6-dichlorohept-5-ene 2,1. At first glance, it's just a jumble of letters, numbers, and dashes, but that name is a perfect set of instructions for building this exact molecule. So how in the world do you get from that to this? Well, that's the mystery we're about to solve. And here's the really cool part. You don't need to be a chemistry genius to figure this out. What if you could learn to read it right now in just the next few minutes? The secret isn't about memorizing thousands of insane rules. Nope. It's all about understanding just 3 key parts that make up pretty much every single organic chemical name. Okay, so before we dive in and crack the code, you might be thinking, why does any of this even matter? Why can't we just give molecules nicknames? Well, the answer is pretty simple. In science, and especially in chemistry, clarity is everything. It's about creating a single, universal language that everyone can speak.
And look, don't just take my word for it. The official governing body for chemistry, a group called IUPAC, puts it perfectly. This system is a key tool for everything from scientists sharing research to global health and safety regulations. Having one shared language prevents really costly and sometimes straight-up dangerous mistakes.
All right, it's time for the main event. We're going to pull back the curtain and finally crack this code. And like I promised, the secret isn't some huge, complicated rule book. It all boils down to those 3 simple parts. And this right here, this is the secret. Every single one of these super complex-looking names is built from just these 3 fundamental pieces. You've got a prefix, a base, and a suffix. If you can understand what each of these 3 parts does, you've basically unlocked the entire system. So, let's start with the foundation, the base. The base is the absolute core of the name. All it does is tell you how many carbon atoms are in the longest continuous chain. Think of it like the molecule's backbone. It's just like how oct in octopus means 8, right? Well, in chemistry, pent means 5 carbons, hex means 6, and so on. That's it. That's the base. Next up, we've got the suffix. This is kind of like the molecule's last name or its family name. It tells you the single most important chemical feature on that molecule, which decides what family of compound it belongs to. So if you see all at the end of a name, you know, boom, it's an alcohol. If you see -one, like in our mystery molecule, you know it's a ketone. The suffix defines the molecule's whole identity. And finally, we have the prefix. This is where all the details go. The prefix describes all the other attachments, all the little groups that are hanging off that main carbon chain. It tells you what they are, like a chloro group or a methyl group, and crucially, it uses numbers to tell you exactly where they're located. Okay, so you've got our 3 parts. Prefix, base, and suffix. But how do we actually put them to use? Well, the first and most important job is always to find the molecule's main structure, its backbone. And there's a really logical order to this. First, you scan the molecule and hunt for the most important chemical feature, the most senior group. That's going to decide your suffix, your family name. Once you've got that, you find the main carbon chain or ring that it's attached to. That gives you the base name. Everything else is just a detail we'll add on later as a prefix. And don't worry, there are rules to help you decide. For instance, there's a simple seniority rule for choosing the main structure. If you have to pick between a ring of carbons and a chain of carbons, the ring is usually considered the senior one, the more important one. It's just a simple rule of thumb that helps keep everything consistent. So, once you've found your main parent structure and you know what its most important group is, it's time to add in all the other details by assigning the right prefixes and suffixes. Now here's what's so cool about this. There's actually a hierarchy, a pecking order, for all these different chemical groups. The group with the highest seniority, like a carboxylic acid, which is at the very top of this list, gets to be the suffix. It wins. Every other group on the molecule, it doesn't matter what it is, gets demoted and has to be named as a prefix. So let's just recap the big rules here. 1, the most senior group, the king of the hill, gets the suffix. That defines the whole molecule. 2, every other group becomes a prefix. 3, you list those prefixes in alphabetical order, and this is key. It's alphabetical, not by number. And 4, you use numbers called locants to give everything an exact address on that main chain. Okay, enough with the rules. Theory is great, but let's see this system in action. We're going to walk through naming a molecule from scratch, putting all these pieces together step by step.
All right, let's try to name this molecule right here. It looks pretty branched, a little complicated, but if we just apply our three-part system, we can give it a single, totally unambiguous name.
Okay, step 1. Let's find the base. We need to find the longest continuous path of connected carbons. If you trace it out, you'll see the longest possible chain has 7 carbons. The base name for 7 is hept. And since all the connections are single bonds, the full parent name is heptane. That's our base. Easy enough.
Step 2. Numbering. Now, we have to give all those carbons an address. The rule is simple. You start counting from the end that gives the attachments the lowest possible numbers. If we start from the left, our first attachment is at carbon number 2. From the right, it would be at number 3. So, 2 is lower than 3. We start from the left. That's the correct way.
And now, step 3, let's identify our prefixes. We just look at our numbered chain and see what's hanging off of it. On carbon number 3, we have a little 2-carbon group, which is called an ethyl group. And then on carbons 2, 4, and 5, we have these little 1-carbon groups. Those are called methyl groups.
And now, we assemble the final name. Remember, we list the prefixes alphabetically. Ethyl comes before methyl in the alphabet, so it goes first. We have an ethyl group at position 3, so we write 3-ethyl. We have 3 methyl groups, so we use the multiplier tri for 3, making it trimethyl. And where are they? At positions 2, 4, and 5. So 2,4,5-trimethyl. You put it all together in front of our base name, heptane, and there it is. 3-ethyl, 2,4,5-trimethylheptane. Just like that. Code cracked.
So you see, it's not a random string of syllables at all. That name is a precise, logical, and totally universal set of instructions. Any chemist, anywhere on the planet, can read that name and draw the exact same molecule we started with. That's the real power of this system.
Now we've really just scratched the surface today, but you now have the fundamental key: prefix, base, suffix. Yeah, there are more rules for more complicated situations, but they all build on this simple foundation. So the real question is, now that you know the basic code, what other chemical names are you going to see out there and be able to decipher?